Today we will discuss statically indeterminate problem. Already we have discussed what is statically indeterminate problem earlier. Now here our job is how to handle that type of problem. Now if I write structure in two form, though we have written it earlier, still we write here a structural problem. So it is just two groups, statically determinate, statically indeterminate. The division is made basically on the idea of equation of statics. Any problem, there are some equation of statics. If we take a three-dimensional problem, we will have 6 equation of statics. If we take a plane problem, it will have 3 equation of statics. In space, summation of all the forces along x, y, z, that will be 0, plus moment about x, y, z, it will be 0. In plane, summation of force along x will be 0, along y will be 0, plus moment about z, means moment perpendicular to that plane, so that will be 0. So these are the 3 basic equations. Now if we have a problem where the basic unknowns, which normally we find in the form of support reaction, if it is exactly equal to 3, it is statically determinate, means that problem or those unknowns can be determined with the equation of statics. So we define statically determinate. If the number of unknowns, it is more than number of equations of statics, so that problem cannot be solved. So this problem is statically indeterminate, so it cannot be determined with the equation of statics. Right. Say if we take a beam problem like that, here there is a hinge support, here there is a roller support, there might be any load on that. Now at the hinge, there will be 2 reaction components, so one vertical and another horizontal. In the roller there will be only one vertical reaction component. Now here we can say the horizontal component, it will be 0. Normally in beam problem we take a loading all perpendicular to the axis of the beam. Usually we don't get any component of force along horizontal direction along x. So most of the cases we get it 0. But we can't provide that hinge support as a roller support, because if we put roller on both the side, loading usually it is vertical, so it will take care, no problem. But if there is a small component of horizontal force due to accidental reason, so structure will not be stable in space, it will go on rolling on the 2 roller, so it will not be placed where we want to keep it. So for any unknown or undesirable horizontal force, we have to prevent that, at least left end or right end. So it may be 0 or any small value depending on the type of load, so it should be there. Okay. So theoretically we can say for a beam problem, usually we are not going to take any vertical load all the time, it will be 0. So that horizontal component, all the force, that condition is automatically satisfied. So from the 3 equations, normally one equation is automatically satisfied, so other 2 equations are there. From there we can find out the 2 reactions. Right. Now here the 2 equations are, we can take summation of vertical force along y direction, and we can take moment about this point A, or we can take moment about the other point B. Now if we have some third support here, definitely there will be 3 reaction components plus 1 horizontal component. Normally out of 3 already 1 equation we are taken care of in order to handle the horizontal part. So, vertical and moment part 2 reactions we can determine. So, if we have 3 unknowns and 2 equations we can't find out. Normally the number of equations should be equal to the number of unknowns. If it is more than that, it cannot be determined. Now, I was talking about a taking moment, right. Now, there are 3 forces. One option is we can take moment at one point, and other option is other part is we can take all the forces in the y direction equal to 0. An alternative of that, say if I write summation of y equal to 0 and summation of moment at any point, say if it is A, if it is B, if it is C, we can take ma equal to 0. Other option we can take ma equal to 0, mb equal to 0, that also we can do. Say initially that support is not there. So, we can, if we take moment about this, that we will get, if we take moment about that, the other reaction will get. Now, this may give some idea that instead of taking force, all the forces along y direction, we can take moment about ma and mb, we are getting 2 equations. Now, we have 3 unknowns, but 2 equations we can't solve. So, there might be a temptation that let us take moment about c, okay, or there might be a number of support, we can go on taking moment at different point and go on generating a number of equations. So, it can be theoretically solved, but really if you try to generate that equation, you will find all the equations are not independent equation. Independent means you will find one equation is identical to the other equation. It may not exactly identical, but if you multiply with a factor -1, +1, +2, -2, you will get the other equation, or 2 equations if you combine, you will get the third equation. Just I can give you one simple example. Say 5x plus 7y equal to 10. If I have minus 10x minus 14y equal to say 3, anything actually, right side not necessarily it will be equal. Now, the first equation if you multiply with 2 and add, so x will cancel, y will also cancel. So, in that process you can't find out neither x nor y, none of the quantities you can find out from this system. So, what will be happening, there should be a tendency initially, we can take a moment at any number of points, generate any number of equation and any number of unknown we can solve, but theoretically if you make an attempt, we will more or less getting that type of equations. So, we will basically get 2 independent equations here, okay, apart from the horizontal summation of the force. So, 2 independent equation will get. If you try to generate more, so those equations will be basically coming out from these equations. Maybe this plus this if you add, or this multiplied by 10 minus this multiplied by 5, add, you will get the third equation or the fourth equation. So, whole thing will be not an independent system and equation cannot be solved. So, our main idea is 3 equations, and we may take all in the form of moment, but the number of equation it will be just 3, or horizontal part if we just forget, it will be only 2 equations in the moment form, or 1 moment, another just force form. Now, this problem what I have so this problem what is drawn here basically there are 3 reactions, and we can take equation in this form or in that form. So, the third reaction we can't find out because total number is more. Now, here how the problem can be solved? The problem can be solved in addition with that equation we require some other equation. Say 3 is the reaction and equation of statics is 2. So, we require another one extra equation, and that equation will come from the deformation of the structure or deflection of the structure. So, more or less we are trying to handle deflection of the structure in last 2-3 classes, right. So, those ideas will be required here, and if we use those equations in the form of structural deformation, structural deflection, we will get some information in the form of additional equation. So, apart from these two, we will get the third equation from our structural deflection or structural deformation, and that will help to find out the reaction of the structure. Now, let us take one simple case which is a very popular type of problem. Say this is a cantilever, and here this end is supported. We take any load, say it is distributed load throughout. This part is L, it is EI, we can take it is A, it is B. Right. So, length is L, this end is a clamped support, this is a roller support, fully distributed load, uniform flexure rigidity EI. Now, how many components of reactions are there? First of all, this clamped support will have horizontal component, vertical component reaction, and here there is one reaction. So, 3 plus 1 4, number of equation is 3. So, one unknown is more. So, we say degree of indeterminacy. So, degree of indeterminacy is how many extra. So, 3 is the normal number. So, here one extra is there. So, degree of indeterminacy here it is 1, right. Or if we just remove that support, it is a cantilever beam, there is a load, and that problem already we have solved because it was a determinant problem. 3 reactions at one point, that is support A. Now, due to putting a support here at the right end B, a problem became statically indeterminate one, and it cannot be solved with the equation of statics. We can't determine the reaction, and if we can't determine the reaction anywhere, we can't go and find out the shear force and bending moment, right. So, there is one set of force, that is applied load, another set of force it will come from your support in the form of reactive force. Once all those forces will be known, then only we can come to a particular place, sum of all the force, we get shear force, or we can take summation of all the force in the form of moment at that station, we will get bending moment there. Now, the main job here is to determine the reaction. Once that will be obtained, we can find out anything inside. Now, how the problem can be handled? Now, this problem we can just write in this form. Say it is a cantilever problem with that load plus that roller here, it will give a reaction RB. So, at B there is a roller will give a reaction force is R, at B, RB is the reaction, and this force normally, this omega is the load per unit length, intensity of distributed load. That value will be a known value, some numerical value will be given, because that is the external applied force. Now, this RB, this force will be supplied by the support in the form of reaction, and that force is unknown here. Okay. Now, this problem can be solved in two steps. So, this may be divided as already we have talked about method of superposition. If a structure is subjected to more number of load, we can get the effect of the individual component of force, then we can combine their effect through simple algebraic addition, that we say it is method of superposition, because whole thing is a linear system. Now, here there are two load, one is omega. So, first step we have put this distributed load, and this RB we have removed, that we are putting in the second level. So, this RB, that force and this force, they are applied separately. So, deformation of the beam are subjected to W and deformation of the beam subjected to RB. If we combine, we are supposed to get the deformation of the actual structure. Now, due to omega, it will take a shape like this, and due to RB, it will take a shape like that. Now, here if we say this is your delta due to W, and this is basically delta due to RB, these two values should be equal and opposite, because in a real structure joint B is connected to a support. So, it can't move vertically upward or downward. So, under W, whatever W delta W will get, that should be compensated by RB in the form of WRB. So, if we take it is positive, it should be negative. If it is 2 millimeter, it should be minus 2 millimeter. Ultimately, whole thing if we combine, we should get back to the original situation where deflection at B should be 0, right. Now, this delta W, delta RB, the deflection values already we have determined. If we take a cantilever, at the end if we apply a load, whatever deflection we will get, or if it is fully distributed case, whatever will be the standard value, that already we have determined. Now, we can write this value here again, delta W. So, it is fully distributed load, and that value was already we have determined, it is omega L to the power 4 divided by 8 EI. So, it will be omega L to the power 4 8 E I. Now, this force will be how much? It will be R B L Q divided by 3 E I, right. Now, these two deflections should be equal and opposite. So, if we just equate these two equations, we can find out RB in the form of your W, L, E, I, something we will get from there. Okay. Now, next step, if we just equate that, your delta due to W should be equal to delta due to your RB, and this we have written as so from there RB will get, it will be this L, this 3 divided by 8. So, EI will cancel, LQ will cancel, it will L remaining, omega will be there, 3 will go to that side, 8 is below. So, 3 by 8 omega L will be the reactive force there. Now, if I draw the beam again, So, actual structure, it can be represented by a simple beam without the support at the right end. In lieu of that, we will supply the reactive force supplied by the support. So, the reaction supplied by the support is RB and the value we have calculated is 3 omega L by 8. So, total load is omega L on the beam, and it will be 3/8 of that, it will be coming in the form of reactive force there. Now, at any point, if you try to find out the shear force, it will be your 3 WL by 8 minus omega into x, right, or moment if you want to take. So, this 3 WL by 8 multiplied by x minus omega x square by 2. So, this plus or minus depending on the sign, effect of that can be taken as plus. So, effect of this will be minus, or it may be reverse. So, you can draw the bending moment diagram of the beam, you can draw the shear force bending moment of the beam. Finally, we may be interested for finding out the maximum stress, right. We will be interested for finding out the maximum shear stress. So, all this quantity we can find out from the structure. So, the main bottleneck was number of reactive force was more, and in a normal way we could not proceed. Naturally, we had to take the help of deformation of the structure. So, we have tried to match the deformation. So, this technique sometimes we say it is a consistent deformation technique, means structure will have a deformation, it will maintain some consistency because there is a support. So, deformation should be equal to 0, right, or somewhere there might be a support, left side right side slope should be equal or deflection should be equal. So, some form of deformation compatibility we have to establish. So, basically your this displacement part we have to take care, and we have to get a additional equation. Now, in the next case, if we take a problem like this, say let us take a simply supported problem. It is fully loaded with omega, and I am making it quite simple. So, L is the span, L is the span, right. A, B. So, it is A, B, C, this side is L, this is L, fully loaded omega. Now, already that problem was defining, because there are 3 vertical reactions plus 1 horizontal reaction, though that will be 0, but we have to take. So, 4 is the total number of equations, 3 equation of statics. So, our extra equations we require is the extra number of unknowns. So, extra number of unknowns that we are defining in terms of degree of statically indeterminacy. So, degree of statical indeterminacy, here it is 1. So, at least one additional information in the form of some equation we should get for finding out these reactions. Now, this problem can be handled like this. Now, say at this level we remove the central support. Now, due to that we will get some deformation here. Now, we are not supposed to remove the support at the middle. To take care, we have to supply a reaction, say RC. So, in actual case this omega will be there, plus there will be a reactive force at C due to the this roller support. So, if we want to remove that, we have to take the effect of that in the form of some reactive force. So, that is RC. So, that we are putting in the second level. So, if we combine, we are supposed to get the actual structure. Now, due to RC, the beam should deform like this. Okay. Now, whatever deformation you will get here again, if we say this is delta for omega and this is the deformation whatever we will get delta for your RC. Similar to your earlier case, this value and that value should match, right. So, if we write your delta this value should be equal and opposite, and that opposite part that we have already drawn here. So, we need not bother about the sign because sign part is reflected through drawing. Now, this delta omega, delta RC, these values are, this is a simple determinant problem, a simply supported beam fully loaded. So, central deflection we know already, we have the expression. Now, here also it is a simply supported beam with a central load, and for that problem also we have the standard expressions. Some of the cases we have derived, some of the cases anytime we can derive with our basic understanding in the form of differential equation technique or moment area theorem, or we can just consult some standard table, from there we can pick up. So, what will be this value? Omega L. Omega L will be your 5 omega L to the power 4 divided by 384 EI. Only this L part here, it will be L and L, it will be 2L. So, it will be 5 omega and 2L 4 divided by 384 EI, and that should be equal to this will be R C 2L Q divided by 48 EI, right. So, it is PLQ by 48 EI, and this will be 5 omega L to the power 384 EI. Only L part in this problem is equal to 2L, just we have substituted that. Now, from here this RC can be easily determined, just we have to put the expressions. So, if we just simplify that equation, so your RC will be it will be 5 omega, and 2L part it will be Q and 4 it will cancel, 2L, and it will be 384 and this 48 that will go off, so it will be multiplied by 48, right. So it will be 4, 8, 0 on the numerator, because 5 into 2, 10, 48, it will be omega L divided by 384. I am sure it can be further. It will be 5 by 4, right. So that will be its reduced form. Now I can draw the beam again. It will be 5 omega L by 4, and total length is equal to your L and L, so twice L. So the support we have first replaced in the form of some reactive force unknown RC, and that RC we got 5 W by L divided by 4. So it is a simply supported beam with a vertically downward applied fully distributed load, plus at the midspan there is a concentrated load, value is known, but that value is acting in the upward direction. So this problem can be easily solved, the remaining reactions, and you can find out shear force, bending moment, shear stress, bending stress, any important information you want, you can find out from there. So far we are handling a problem where the degree of indeterminacy is 1. So extra unknown is 1. So cantilever beam, the end reaction we have removed. Here the central part we have removed. Here I want to mention the central reaction we have removed. So not necessarily that is the only alternative. So if we come to the original problem, so here this was removed by a force. We could keep the support, remove this one, and put a reaction here. That can be also done, or we can keep this support, remove that, put a reaction there. Or if I take the cantilever problem, we have removed that. Here the restraint against rotation we can release. So we can make it simply supported. We can make it a hinge support with a applied load, and that load will be in the form of your bending moment. So one bending moment will be acting at the end, and that bending moment is an unknown quantity. So it will be a simply supported beam, fully loaded, plus a end moment. So one extra quantity that, so there due to the fully distributed load there should be a slope, and due to that moment slope will be in the reverse side, right. So the vertical load, it will try to make a slope like this, and this moment it will give a slope in a reverse manner, and it should be equal and opposite, because it is a fixed support, so slope should be equal to 0. So in that manner, not necessarily this is the only place where we can remove and put the load. There might be some other possibility. So same problem can be solved in different manner. But all the cases, our extra unknown degree of indeterminacy is 1. So we are writing only one equation, we are trying to match one deflection, and from there we are getting the result. Now once we have solved two problems, two different type of problems, now I want to take a beam where at least the number of unknowns will be more than 1. So your degree of indeterminacy will be 2. So we can take a very simple type of problem. say there is a beam, it is fixed at both the end, right. Now there is a load, and this load is acting here. And this part we can say here to here is A, here to here it is B. It will have EI, L, everything, and we can say L is nothing but A plus B, and it has some flexural rigidity EI. Okay. No, it will not stretch. So the right end is fixed along with the left end. So if we remove the right end, it will be normal cantilever beam determinant. So if you remove the right end, how many reactions you will just eliminate, or you have to take in the form of some reactive force. First of all, it will give a vertical reaction force, plus there will be a rotational part. Now horizontal part we are not considering, because there is no horizontal force, and we say this horizontal force here and here it will cancel. Okay. So basically we have two equations apart from the horizontal equation. So two equations, we can take one vertical reaction, one moment. So one vertical, another rotation, that part will be extra. So two additional unknowns are there. So degrees, your degree of indeterminacy is equal to 2, right. There is another possibility. We can just make both the clamped support as hinge support, take some reactive force and allow the rotation. So it will be a simply supported problem with moment. So there, if we say it is A and if we say it is B, so there will be a moment MA, there will be a moment MB. One option. Another option is we straight away remove that support and take a vertical reaction and a moment, right. So in two ways we can handle the problem. Now this problem we can say, if I idealize in that manner, right. So we can release the release the restraint imposed by support A and support B against rotation, and put some moment in lieu of that resistance or that restraint. So restraint will basically give some moment. So that moment, say we have given in the form of MA, and moment here it is MB, and just it was converted to a hinge support, but our requirement is we have to find out MA and MB. Now this problem can be divided into component. So if we put the load here P plus Now due to that load there will be a deformation like this, and due to the applied moment MA and MB, it will try to bend in the upward direction. Okay. Now the second part, we can put in two different steps also. We can put P, second step MA, third step MB, or here MA, MB, second, third we have more or less combined, right. So more our maturity will come, we will try to combine the effect. We will just imagine this is happening, so we need not break the different steps. So it is better to break in some steps at the beginning to get a feeling what is happening. Now here, due to that load P at A, we will get some slope, at B we will get some slope. Now this slope at A will be produced by the load P only. Now due to MA and MB we will get some slope here. So this slope should be balanced by this slope, because in actual structure there will be a clamp support, slope will be equal to 0. Similarly here slope and slope, it should be balanced together. Now two additional unknowns we have taken in the form of MA and MB, and these two unknowns can be evaluated from the compatibility of slope at A, matching of the slope at A, and similar way we just equate the slope at B obtained from here and here. Okay. So basically slope compatibility at A and B we will try to impose, and from there we will get two information in the form of two equations, and these two equations will help to evaluate MA and MB. So two unknowns at two places we have to look after the deformation of the structure, right. Now intentionally I have put the load in a very arbitrary place, so distance is A and it is B. In a special case, if I put P is equal to at the center of the beam, say it is at L by 2, in that case MA should be equal to MB. So we could calculate only one quantity, only matching with the slope at A or B. But if we make it unsymmetrical, definitely your slope will not match this side and that side due to P, and your MA and MB will be different. But anyway, if we handle a general case, we can make A is equal to L by 2. So a specific case can be determined from there. Okay. And there should be a checking, MA should be equal to MB. Now these two steps let us find out. So we just draw it here again with some notations. So the first part, and there is a P. Now it will deform like this. So we are talking about that this is A, this is B. So this angle will be your, say, theta A due to, say, P, and here it will be theta B due to P. So there is a superscript P to identify this is responsible for P only. Now this theta A and theta B, that you can derive from with your earlier concept of moment area theorem or differential equation technique. Here the theta A and theta B, it is available. So theta A, if I put here theta A P, it is given P B L square minus B square divided by 6 L EI. So 6 L EI is the denominator, P B L square minus B square is the rotation at the left end. This part is A, this is B, total length is L. Already we have written that. Now this equation and theta B due to the P, that part is PAB 2L minus B divided by 6 LEI. Right. Now this is the rotation at this end. I want to change this expression a little bit, because A plus B is equal to L.
In terms of that.
Now the numerator part I want to keep entirely in terms of AB. Denominator it will be L, because there some part is A, some part is B, and if we express that, you will find expression will be more or less similar type. So it will be identical expression. So here we can write P. So L square minus B square you can write as L plus B, L minus B. So L minus B is A. L minus B will be equal to A. So this A, if we take common, so it will be AB. So here AB is there. I want to bring it there. Okay. So L minus B already we have taken in the form of A, and L plus B. L plus B. L is what? A plus B. So it will be A plus 2B divided by 6 LEI. Here also this L part P AB, L is your 2A plus 2B. So it will be 2A plus 2B minus B will be B divided by 6 LEI. So what is happening? PAB divided by 6 LEI, that part is entirely identical. Only this end it is A plus 2B, there it is 2A plus B. So A plus B, there is a factor 2. So here this end load is away from A. If we take A is more compared to B, so this slope will be little less. So here it is twice B. So B is small, it is twice B, and this side slope will be more, it is twice A. So if it is P, A, B, A plus B, sum of the quantity will be twice. Which one will be twice? That also from the sense we can find out, plus the denominator will be 6 LEI, that component, right? So this part we can keep in that form, and the other part we took in that manner. So we can draw it here. And there is a MA. There is one MB. So it should be theta A due to moment and theta B due to moment. Right. So theta A plus moment, this is theta A due to moment, it is theta B due to the moment. Now this theta AM, theta BM, they are produced by MA and MB. Now if we take a beam, apply at a moment, the slope will get how much? It is ml by 3 EI.
One end of the beam.
So if you take a simply supported beam, apply a moment. So where we are applying a moment, it will be ml by 3 EI. Other end it will be half ml by 6 EI. If you take a simply supported beam, apply a moment. So if it is not there, if we apply a moment, this angle will be ml by 3 EI and this angle will be ml by 6 EI. Similarly, due to this moment, if that is not there, this end slope will be mbl by 3 EI and this end slope will be mbl by 6 EI. So both the actions are there. So in that case, our theta am, it will be mal divided by 3 EI plus mbl divided by 6 EI, right. Similarly, theta bm, it will be mal by 6 EI plus mbl divided by 3 EI. Can you see that? So it will be mal by 3 EI near end and mbl by 6 EI. It is coming from the moment applied at the other end, because this will be this way, this will be this way, both side it will be just additive. Now next part is this slope and this slope should match and this slope and this slope should match. So if we match that, we will get the reactive force. Okay. Now up to this I am keeping it for this class. So next class, in the next class we will continue from equating these slopes and finally get the reactive force. Gradually we will switch over to other type of problem. In our previous class, rather the starting of the problem was like this. So fixed beam, load placed little bit away from the center. So the load, bending moment at the two end, force, bending moment separately we have applied. Then due to the load, the slopes we have written, and due to your MA, MB, we wrote the expression of slope at the two end. So next part is just we have to match the slope, because slope here and slope here, it should compensate because it is a fixed support, and here also same thing. So we can write theta A due to P should be theta A due to moment, and theta A due to P and theta A due to moment, the expressions whatever we have written. So if we just write it on the left side, it will be your MA L 3 EI MB 6 EI, that was P A B A 2B divided by 6 L EI. So definitely this part is on the left side, the other part on the left part here, this is on the right side. So similarly at B, due to the load and theta B due to the moment, if we equate, if we write here, so it will be MA L divided by 6 EI MB L by 3 EI that is equal to P A B 2A B 6 L E I. Right. So here it is A plus 2B, here 2B plus A. Here it is 3, it is 6, it is 6, it is 3. So these are the two equations and two unknowns, MA, MB, MA, MB. Now we have to just process these two equations and find out MA and MB. Now the lower equation, if we multiply with 2, so this 6 will be 3 and MA part we can cancel. So this equation we can write, we can straight away multiply, or we can write in a separate line. So it will be MA L by 3 EI 2 MB L by 3 EI. It will be 2 P A B 2 A B divided by 6 L E I. Right. Now if we just subtract that equation, or from this equation if we make it minus, so your MA L by 3 EI part will be cancelled, and here MB part will be remaining, right. So if I come to the next page, say this is your, if I say this is your equation 1, if we say it is equation 2, so if we make equation 2 minus equation 1, so it is equation 2 minus equation 1